Hello, everybody. This is Majid here, the host for the webinar. Thank you for connecting to this webinar. I wish you a good morning or good afternoon, depending on your location. With me, I have Dr. Saurabh Agarwal. He's from the welding team, from the product team. Saurabh, can you hear us? Can you say hello?
Hello, I can
Yeah,
hear you.
perfect. So Saurabh is based out uh, in the Calcom office. So that's in Switzerland, right, Saurabh?
Yes,
Perfect. Okay. And I'm based out in India. So I'll be here. So if you have any questions or if you're not able to hear the webinar, so just use your chat window, just raise your hand and I'll be there to check it out for you. Um, this webinar is about welding, and I think Saurabh would be the better person to introduce you about the topic. But just a note that should you have any questions or any direct query, you can write to Saurabh. He's mentioned his email ID right here on his opening slide. So please note it down and you can shoot him an email. So over to you, Saurabh. I hope I have not missed anything. If you need any help, I'll stay muted and you can just give me just call my name and I'll be there to help you.
okay, thank you, Majid. So, thank you, Majid, and for the participants who are joining from Europe, a very good morning. And I noticed that we have some participants also from Asia, so very warm good afternoon to all of you. So, today we are very pleased to present you that how we can control the distortions in car body manufacturing using virtual welding and assembly simulation. So before I start, I also take the opportunity to introduce myself a bit. So I am Saurabh Agarwal within ESI. I am responsible for worldwide product marketing and business development for welding and assembly solution, which is well known as ESIWeld. As Majid mentioned, I am based in Qualcomm office in Lausanne, Switzerland. So I have been working with the ESI group since last 5 years. And before moving to ESI, I did my PhD from Swiss Federal Institute of Technology. It's in Lausanne, Switzerland. So let's start. So just to present you the brief outline, so we will be talking very briefly about the key automotive trends and the challenges for the body shop where the car body is manufactured by welding and assembly, and how we can accurately predict the distortions in the welded assemblies. But predicting the distortions is not only the objective is to how to control the distortions, and we will demonstrate with a few industrial examples. And then in the end of the webinar, there will be a live demo for just to show you the workflow. So let's start with the automotive trends and key challenges for body shops. So I hope you all will agree with what I am going to say, because these are the general trends. So as you know, due to the global warming, automotive industry is forced to follow strict emission norms. And due to these emission norms, to follow these emission norms, weight reduction and electrifications are the key levers for achieving CO2 emission targets. And these are the main levers which automotive OEMs and tier suppliers they are adapting. And along with the emission norms, safety concerns, they are also the requirement of safety is also increasing day by day. And uh, over the decades, due to the tough competition and industry transformations, the cost and time to market remains one of the key performance indicators for the industry. So in the nutshell, these are the um, four key areas, weight reduction, safety, cost, and time. These are the key factors for their performance for both OEMs and their tier suppliers. So let's discuss a few challenges and the requirements for the automotive industry to how they can overcome these challenges. So we say back to the basics, maybe the vehicles in the future, they are electric or not. We still require basic parts such as wheels, seats, chassis and bodies. And especially this today's topic is car body manufacturing. So it's body in white. Um, so the design cycle of the car platform is reduced from several years to months. So that means one needs to save on building physical assemblies and do only effective things that also most efficiently. So that means we need to ensure successful upfront verification and validation to avoid costly downstream problems. Means at the design stage, we need to include the manufacturing effects or defects so that we avoid them or we control them at the production site. So this is really the one of the aim of the industry. And as I mentioned, the weight reduction is one of the levers for the uh, emission reduction. So advanced steels, they offer the best weight reduction to saving ratio for automotive parts, but often they possess more spring back as and less formability, which leads to their manufacturing challenges. So that means they cause advanced lightweight materials, they cause dimensional inaccuracies in the welded assemblies. And as you will agree, the manufacturing effort due to all these advanced materials and the manufacturing processes, it's increasing day by day. But cost and time to market must reduce. That means industry, they need virtual solution to help their engineers to simulate and mitigate the defects right at the design stage when there are no physical prototype exists. So that means all the manufacturing knowledge has to be put at the design stage itself. So just to demonstrate you or just to discuss about the few key issues in the automotive industry and what is their the main objective to ensure the dimensional accuracies in the welded assembly. So normally in body shops, the stamped deformed components, they come from the press shop. In the body shop, the stamp components are positioned in the RPS system, which we say reference positioning system, and then they are holded together for gap closing, and then finally they are joined to form an assembly. So the end goal of any body shop engineer is to manufacture the stamp weld assemblies within the right tolerances to ensure the dimensional accuracies. So, but often they encounter dimensional inaccuracies because of the two main reasons. One is the mechanical load effects of the assembly, another is the heat effects of the joining process. And also the body shop engineers, they have to deal with lot of challenges, like there are multi materials and they don't have they don't have same behavior in terms of thermal and mechanical. They have to deal with the stamp components which do not fit the CAD nominal shape, and they have no control on the stamp shapes because they come directly from the press shop. And they have to also deal with the unexpected gaps between the components and parts which are deformed. And they have to also deal, as we mentioned, the heat effects of the welding because of the thermal expansion and contraction during joining. So these are really the key day-to-day life of a body shop engineer. So in order to avoid problems, the body shop engineers, they need to tweak the production and its production process multiple times before the distortions and dimensional inaccuracies or dimensional accuracies, they are within the tolerance. So within these specifications itself. So the main objective for body shop engineers are that they would like to maybe I point out. So they would like to ensure they want to optimize the positioning and holding system as soon as possible or as fast as possible in order to reach the requirements. Optimized weld position and sequences. They want to identify the critical joints before the physical prototype is built, and they want to take countermeasures at the design stage, so that they are aware what problems might happen in the production, and they are already taking the countermeasures. And the most important, they want to keep the distortions of the assemblies within the inside the tolerances. Means we cannot say that there will be zero distortion. The distortions are bound to happen, but the goal is how to control that they are within the specified range. So all those objectives and the pain points, they can be met easily by ESI welding and assembly simulation solution for distortion control and car body manufacturing. And this is what we will be presenting. But before we move, just to show you a typical issue in the automotive body. So, and you will agree that these issues, they are very difficult to predict at the design stage when no tools are built. So it's just a prototype part cowl plenum assembly in body in white. So as you can see here, so the reference positioning system, they are planned during the design stage when there are no tools. But due to the stamp deformed parts, there are often interactions or interferences between the parts and the RPS system. So here in this uh, image, you see that such interactions, they are difficult to anticipate at the design stage. So that means body shop engineers, they have to take care how to avoid these things. And moreover, during the assembly, there are large gaps, and it's not possible to close such large gaps by hand. That means closing such gaps in the body shop will then lead to distortions, which you will see in the coming slides later in the presentation. So let's now talk about how we can accurately predict the distortion in welding assembly with the simulation software which we have, ESI welding and assembly solution. So just to give you the overall view of the different steps which are taken, so that's the main goal of this slide. So to fulfill the objective of body shop engineers, we have developed a dedicated solution for distortion control for car body manufacturing. So it's an easy to use assembly simulation software that covers complete manufacturing chain, starting from stamping, pre-positioning, holding or gap closing, and then finally um, welding and joining, and to support also the performance analysis. So it helps the process engineers to control and validate the distortions and also the product performance by taking into account the manufacturing effects right upfront at the design stage. So as you can see, or you will acknowledge also that during this complete chaining simulation, as the model will be changing and it needs to transport key data from one simulation model to another, we need to map the results from stamp to pre-positioning to holding and finally to joining. So to reduce all these things, reduce all these chained process, we have also developed a dedicated tool which is already implemented in the software. So in the next slides, we will explain a little bit more about the solution and its application. So here we would like to present a complete end-to-end simulation chain for complete manufacturing for B-pillar case. It's important structural component of body in white. So here the stamping simulations, they were performed with the ESI solution PEM stamp, and the key results, they are plastic strains, stresses, and variable thickness. So in just to make it clear, so there are two ways you can use the software welding and assembly. One, you can do the stamping simulation if there are no tools existing, or you can already take the deformed components coming from the press shop, and that can be your starting point. This will be presented later in the presentation. So here in the pre-positioning or positioning stage, so started with the stamped deformed shapes, the parts they are positioned in the RPS system, which is a reference positioning system. So we have developed a complete workflow to help the end user to set up the complete model by defining different locators, guide, positioning tools or support structure, and also the contact management um, to simulate the pre-positioning. So user has also the options to choose from various predefined positioning tools. So this you will see few of these tools in the in during the demo. So I don't show it here. And moreover, it's also possible to import automatic import of clamps and locator tools from user defined files, because most of the OEMs which we are working, they have their own standardized way of storing all the or creating the reference positioning system. So it's also possible the automatic import of these RPS system. So here you can see in the RPS, in the RPS system, the parts they fall under gravity, and we can simulate the displacement and the residual stresses because of just positioning stage. So once the parts they are positioned in the RPS system, the components they are holding together to reduce or to close the gap. And user here can define different holding and clamping tools. So here the gaps they are properly closed before any joining operation. So here the based upon the sequence for various closing tools or clamping tools, you can you can define the sequence as per your requirement. And mostly the clamps they are piloted by force and displacement criteria. So here again the user get the possibility to simulate the displacement and stresses. So here if you see closely, the different holding tools they are closing the gap step by step, and we get the displacement and the final stresses. And then moving further, once the parts are positioned in the RPS, the parts they are holded. Now there is a time to do the joining operation. So here user can define the welding sequence. So during this computation, the components will be connected, and user have the excess of distortions and the stresses, because of the complete process. It's not only about the joining, it's the complete we take care of the all manufacturing effects, right from the stamping, pre-positioning, holding, and joining. So here also you have the possibility to define the weld sequence based upon your requirements. And once you have all the information, you have the possibility also to compare your final assembly with the nominal CAD and visualize the distortions in a ESI environment. It's and here you can see the red color. It shows the inaccuracies in the system, and based upon such visualizations, you can decide, you can make corrective decisions. So moving further, coming back to the problem which we stated in the cowl plenum, where the real deformed stamp components they were given to the body shop, and then the body shop has to find out what can be the issues or which are the critical joints. So you will see in the next slide. So here in this particular case, the real deformed stamp components they were scanned with the white light scan as manufactured by the press shop. So that means the white light scans they provide realistic gaps including stamping manufacturing history. So the body shop has to ensure the tolerances of the final assembly. So that means what we did, we from the STL file or the scanned file, we created the meshes, the working surfaces of the positioning system. They were extracted from the CAD files. Here you can see the holding stage, it's a complete RPS system. And the assembly, what is very important to say, the assembly simulation or welding assembly simulation is performed on the deformed geometry, not on the nominal CAD geometry. It's really the stamp deformed geometry, which is very important. So of course we have all these stages from stamping to pre-positioning, holding, joining, and releasing. So what is somehow the most important thing which we can see here, that the gap closing, it will lead to high distortion. So with this simulation tool, you can identify the critical gaps that will lead to the distortion. So in this particular gap, you see particular case, we see like what you see here is the undeformed model is shown in the dark blue, and so it's 10x zoom, and you see there are high distortions. And what we can see that these distortions, they are led by this critical gap, means so we can already identify at the design stage or at the stage before doing any assembly, that which are the critical gaps, and then we can do we can perform distortion engineering on the critical gaps, not all of them, so and take countermeasures. So that means the virtual engineering is capable to predict major distortions at the extremities after welding and unclamping within the tolerances based upon initial gaps. So now, of course, it's very good to say that we can predict the distortions, but the final aim, as we mentioned before, is really to control these distortions, that the assemblies, they can fit within the required specified tolerances. So in the coming slide, we will demonstrate a few applications, not going so much into detail, but just to give you the overview that how one can control the distortions using using virtual assembly and welding and assembly simulation. So here what we show one example of a typical door case. It's also a body in one structural part. So where we will demonstrate how the pre-bending of the part is useful to reduce the final distortions. Here again, means we stamp the parts, and then during the holding stage, we pre-bend intentionally the part by 7 millimeters. So if you see in this particular, that the part is pre-bent, and one can compute the pre-bending stresses to ensure that they are within the limit, and you will see what was the reason to pre-bend the part. So it's mainly the compensation based upon the pre-bending. So during holding stage, as I mentioned, we pre-bend the part minus 7 mm, and due to the heat effects of the laser welding, the parts, they were distorted plus 6 mm. But as we can see, in the end, the final geometry was fitting the nominal geometry. So it's more or less fitting the original CAD or the required CAD. So what is the message for this particular case? That with such simulation tools, we are able to numerically know the amount of pre-deformation required in order to prevent the distortions due to stamping and welding processes directly at the design stage, when no physical prototypes they exist. So this is really one of the way to compensate the geometry based upon pre-bending. Another so welding distortions, they can be also controlled by the weld sequence, by changing the weld sequence, and we have a dedicated tool for that, the weld sequence optimization. As here the user, of course, they define the original the initial weld sequence, and based upon so in the workflow, user can define the weld sequence and also the user defined constraints. And due to the complexity of the problem, we have developed a genetic algorithm based optimization for minimizing the distortions by weld sequence optimization. So finally, what we see, like we get the weld sequence which will lead to minimum distortion. So here in this particular example, we were able to reduce 50% based compared to the baseline, and 25% improvement in the distortions compared to the worst case. So it's really a good tool, means to control the distortions by changing the or optimizing the weld sequence. So this is somehow, and all these things you can do before doing any real assembly process. So you have a very good knowledge when you are doing the final or the real prototyping, real production, so that you don't make any mistakes, and you are sure that the assembly will be fitting the required tolerances. Okay, so let's talk about short live demo. Okay. So the goal of this demo is just to demonstrate the overall workflow, means I will not go so much into detail and how to set up the model, but just to show the overall all the different steps which are required. So here, so this is our visual environment, which is the, let's say, the key platform for our all the softwares from ESI, and of course in this case particularly visual welding and assembly. So as you can imagine, the simulation is performed in 3 different stages: pre-positioning, holding, and joining. So we have dedicated advisors to help you to set up the complete model. So I will not be going so much into detail about pre-positioning and holding. The most important is as I mentioned, to show you the overall workflow, and I think the best is I go in this advisor. I have to close this thing. Okay, so here we have 3 parts or 3 components to make the assembly: the external component and 2 internal components, and it's made up of the material is tempered steel S355T. So what is so the first stage is to create the RPS system. So how we create? So you have different locators and the positioning tools. So I will just quickly create one simple locator to demonstrate that it's very easy to create. So you create the you select the reference component, you select the base point center of, let's say, this particular, and then you define the axis. Maybe in this particular case we can say standard y-axis, let's say 5, height is 20, element size 1.2. So it has created one locator. So it's very easy to create such RPS system, and as I also mentioned, there is a possibility for automatic import, so from the mainly the Excel files, and same applies to to the positioning tool. So you can create the positioning tools in the similar way as we have created the locators. So what is important to show is you have different sorry, you have different shapes which you can choose, so as you see, you have circle. Maybe I create a few of them, so just to demonstrate. Select this. So here you can see the shapes, they are changing, and then you have different possibilities. As I mentioned, you have circle, rectangle, square. So it's based upon your requirements. You can create different different positioning tools and also different holding tools. So as in this particular example, we have created many positioning tools. And then you can define the clamps. Here we have the possibility to, we have defined the elastic clamps. And then once the holding and positioning tools, they are defined, we define the spot welds. So here you have the possibility to define all the spot welds. So depending upon there will be some spot welds which are associated with the three parts, so they have two different connections. So you can see all the spot welds which have been created for this particular case. Okay, force and pressure we don't use in this particular case. And then we have the gravity definition. So for pre-positioning and holding, we do define the gravity, and for the joining, we don't we disable this option. What is important is also before any running the simulation, you can see the complete sequence. So here, what we see, these spot welds, they are defined one weld per step, and accordingly you have all the positioning tools, they are activated and they are released slowly. Once after the spot weld, they are released to see. And what is important, you can, maybe I make it slow so that you can, okay, put the clamps as well. So here you see the complete let's say the sequence of all the positioning tools, spot welds, and so this is required before any, let's say, the simulation, means you can ensure that your model setup is correct. And when we will see also the yes, so and after the spot welds, there is release of the positioning tools and the clamping. And another important point before launching the simulation is the contact management. So for each connection, we automatically define the master and the slave. And what is important to note that the arrows, or they should be always from master to slave direction. So if we see in this particular direction, So master arrows, they are towards slave, and slave arrows, they are towards master. So this is somehow the important requirement, and it's for each but these things, they are automatically done in the software, but you just need to ensure that they are the directions of the arrows, they are correct. And once you have created all the model, then you can run the simulation, and thanks to our DMP solver, you can run the simulation on multiple processes, Okay, so maybe I will just show you the also few results. So then we shift to our visual viewer environment to see the results. I just open the file. So, so here what we load the result file, and it and within some hours you get the complete result from pre-positioning, holding, and joining simulation. For this particular case, for 3 different stages, it took 2 hours only. So we just see first the displacements. Oh, sorry. So as you can see, with each spot weld, the gaps, they were closed, so there were distortions according to that. And in the end, and just go in the last stage, you see the maximum distortion at this point. It's 1.1 millimeter. And similarly, what is important is also you can see the von Mises stresses. So I think this can be interesting, because you will see also the how the stresses are changing based upon the spot welds as it's welded. So it's in the range of 500 MPa, these stresses. And then after all these spot welds, you have the unclamping of the assembly. And one more thing which you can check is also the difference between the your first original geometry and the final. Just open the file. Let's say I make it pink or not pink. And then you can see the object distance. So it's like from point to point difference between the initial geometry and the final geometry. sorry, I need to select the parts as well. Maybe what I do to make it more clear, I go to, let's just focus on the external part. Okay. So I'm just hiding the parts, so that we just focus on the, so here you can see the difference between two parts, but let's calculate the object distance as well. So part, so what this image shows, or the result shows, is the difference, as I mentioned, from each point to on a typical distance between two different geometries, and it's calculated based upon the nodes on the meshes. So I think that's it for the, of course, if you are interested, you can always contact me or our, let's say, the worldwide sales colleagues, and they will be happy to share more details. So let's go back to the last slide of my presentation. I think, I don't know if it should be on. So just to summarize, so it's a tool which can really help the production floors, mainly the body shops, to reduce the cost and time for by distortion control for car body manufacturing. So typical benefits for the product and process architects, that with such simulation tools, as you see in the image, you can we are able to numerically know or predict the amount of pre-deformations which are required in order to prevent the distortions due to stamping and welding process directly at the design stage, when no tools and no physical prototypes they exist. And you have different methodologies or different ways, depending upon your requirement, how you would like to control the distortions. It can be by targeting a new geometry after the stamping, or you can do the weld sequence optimization when the parts they are already made. So it's really depending upon your case to case. And also the solution, it takes into account the complete manufacturing or the all the manufacturing effects upfront at the design stage. So you can identify the influence of gaps and joining process on the on the assembly distortions. You can identify the critical parts and joints before any physical prototype is built, and then you can take the counter measures, not doing a lot of trial errors on the real physical components, but only on the virtual components, which are, I will say, very cheap or very less expensive. So we provide a fast, accurate, and intuitive virtual tool to reduce the overall time and manufacturing costs for welding assembly by taking into account all the manufacturing aspects of this complete manufacturing chain. So I thank you very much. So as Maji said, please feel free to contact me by email, or please visit this website, and you can contact our sales, which is located almost in many countries. So you have all the local sales and local technical support, which will be very happy to help you to explain or go more into detail about the solution, and they can organize demo and detailed demo. So today what I showed, it's just the workflow, and but it would be interesting for you to maybe go into more details, and we will be very happy to assist you for that. So thank you from me. Maybe Majid, you can take the lead.
Thank you, Saurabh, for the presentation. As mentioned, if you have any questions or any comments about this presentation, please drop a line to Saurabh. He shared his email ID on the slide. And to stay updated on the latest webinars or events, please visit our website, and I'll just drop a link here. That's where you can find all our webinars or events those are happening. So good luck to everybody, and thanks again, Saurabh. Have a nice day, you Saurabh, and
Thank you very
to all
much,
the
Majid.
attendees. Yeah, to all the attendees, wishing you a good day or good evening as per your location. Okay, thanks. Bye.
Bye bye. Thank you.